called me, and she's got a business process improvement position open. So if you know of somebody, I think we'll be sending out a listserv thing, but let me know if you know of somebody that's looking. So we're going to be covering the first lecture in Chapter 3, and that's kind of the building blocks of the rest of the semester. And so the concepts don't seem that hard, because they're not, but they're important that you get the fundamentals. So that's really, we're just going to start with very simple fundamentals here today, and then we'll continue to kind of expand on those as the semester progresses. Okay? So due then next Monday night, you'd have the 2A homework, right? And probably about half of you finished that up yesterday, it looks like. And then you'll have the 3A homework, which will be a series of short problems based on what we're going to do today in class. And then you'll have your goal, your chapter 6 through 10, those questions. I did want to touch bases on the discussion questions. You'll see me go through, and where applicable, I'll respond to that. Or if I've got something that I think, okay, well, you made an especially good point, or there's a point that I want to make in contrast to maybe what you said. The goal, those discussion questions, you're not going to see me say much about that. I do read through them, but I don't respond to them because the premise here is I want you to develop your own sense of things as you progress through the book. Right? And so you're going to answer some questions early on, and I think what you'll find is when you get done with the book, you'll come back and look at some of those questions that you answered, and you'll have picked up some things, and you may answer them differently at the end of the book. So those questions aren't so much about right or wrong. They're about making thoughtful responses and then coming back later on and kind of going back and seeing, okay, well, how has my thought process changed? Because that very last assignment will be go back and look, and in most cases, unless it's someone who's been actively involved in continuous improvement for a number of years, you're going to have maybe a different perspective on how you answer things early on in the semester versus later on in the semester. At least that's my hope, right? You're learning and changing a little bit there. Any questions about where we're at or where we're headed? Nope? Okay. All right, so let's go ahead and start with Chapter 3. And so Chapter 3 is about process flow measures. And so we're going to get into there's 3 basic building blocks that we're going to use throughout the semester. But the chapter starts out with a couple of quick examples of 2 different types of processes. One of them is Vancouver International Airport. And they're well known for their ability to get travelers through their airport in a timely manner. But their focus is on safety, security, customer service. And so their goal is to reduce the time spent in the airport security checkpoints, right, by customers, because we all know that can be a bottleneck when you're trying to get to your plane. And then the other one that they talk about is Bell South. Okay, Bell South International is a provider of wireless. Hold on just a second. I think. Sorry, I've got another file I want to open. I thought there was a couple of things in here that I wanted to address, so sorry for the delay. Yeah. Okay. So, and basically what we know about a process is that it's meant to transform inputs into outputs, right? And so both Vancouver, they transfer passengers waiting to get through the security checkpoint to passengers through the checkpoint, right? That's their transformation process. And so Vancouver International Airport, in 2010, they were named the winner of the best airport in North America, okay? And in order to maintain their service status, they again are trying to improve their process flow. So nobody, even when you're at the top of the pile, there's still room for improvement, okay? Bell South, so they've determined that they are in some South American countries, is where this is from. So they're a provider of wireless services in 11 countries. They have 2 categories of customers, prepaid, which are 79%, and postpaid, which are 21%. And they say that the time-consuming part of that process is the service activation. Okay? And for them to do service activation, they have to, A, determine what type of customer they're dealing with, do a credit check, right? Select a phone and a service plan with the customer. They have to assign a phone number, make a test call, and provide a short tutorial. So that's all part of that process that they do. Okay, but for both Vancouver International Airport and Bell South, right, we have to ask some questions. Okay, and so their questions are: what operational measures should a manager track as leading indicators of financial performance? And again, we've talked about the fact that if I want to measure quality, measuring returns and allowances that can occur over a 10-year period doesn't really help me at the time, right? So from an operational standpoint, what should I measure? How does the time to process a customer and the number of customers that are being served impact the total number of customers that can be served? So what's our volumes, right? Are they consistent? Do we have peaks? Do we have valleys? And how do these process measures impact the financial performance of the process? Okay, and so which specific outcomes, when we do them, can be called improvements, because as you're reading through the goal, what you're going to find out is not every improvement actually makes a difference in customer flow or in process flow. Okay, and how can we prioritize those improvements into an executable plan? Okay, so that's kind of, in a nutshell, that's the course, right? We're going to be looking at how to answer those questions, and that's what's important for both Vancouver and Bell South. So as we go through Chapter 3, okay, the very first part we're going to do is we're going to define what process flow is. In 3.2 through 3.4, we're going to talk about the 3 fundamental measures: flow time, inventory, and throughput. And you are going to hear those so many times this semester. You're going to be singing them in your sleep by the time we're done this semester. Okay, and flow time, inventory, and throughput are the components of Little's Law. Okay, and so we're going to spend 3.5 talking about Little's Law. And so we'll get through 3.5 today, and we'll do some basic examples, and then we'll come back on Tuesday. And I think probably one of the aha moments for me was using Little's Law on financial statements, right? It's not something that I had really thought about, and not something I had done in my career, but it's certainly an interesting approach to looking at and identifying where opportunities exist, okay? And then 3.7 gets us into tack time and inventory turns, and 3.8, how can we link those process flow measures to financial measures of performance? So that's Chapter 3 in a nutshell. And again, we're probably going to get through 3.5 in class today. So the essence of process flow, we have 3 important questions. How much time does a flow unit spend within the process boundaries? Okay. So that's our flow time. So and you can define that as from the point that a flow unit enters the process until it exits the process. That's flow time. Okay. On average, how many flow units pass through the process per unit of time? That's what we call throughput. Okay. And on average, how many flow units are within? If I draw a square or a rectangle around my process, the number of units inside that are the amount of inventory that's in the process at any given time. Okay, so I think I'm going to save that. I have a discussion question, but I think we'll save it for the end. Okay, so here's what that looks like visually. Okay, and so I have one big rectangle around my entire process. The red arrows represent the throughput coming into the process and the throughput coming out of the process. We're going to talk about a stable process today. Little's Law applies when you have a stable process, meaning the throughput of units coming in and units going out is balanced. Right? I don't have way more units coming in than I can push out. Then Little's Law doesn't apply because you get jammed up in the middle. Right? So we've got the rectangle, we've got the throughput going in it. Again, inventory is the amount of units that are inside that process, and that's at a snapshot. Right? So I can take a snapshot of this classroom, and if students are my inventory, I've got 1, 2, 3, 4, 5, 6, 7, I've got 8 students in here right now, right? So that's the inventory, right? And then if we were going to, again, your flow time is, let's say it's a class period, so it's from the time that you enter the classroom until the time that you exit the classroom, right? Okay, and we could use that as a process and map all the steps that we do inside that. Okay, so if I'm going to use a couple of different examples, I might think about a bicycle production line. Okay, and we could say that all the raw materials coming in are represented here on the left-hand side of the diagram. So that's your inputs, right? They enter the process and they're transformed, and all the steps that we're doing in here is what we're going to document. And at any point in time, I can take a snapshot of raw materials, work in process, and finished bicycles that haven't left my boundaries, and that's going to represent the inventory. And then I'm going to have a number of bicycles that are leaving the factory, right? And that's going to be my throughput in terms of units per hour exiting. And it's from the time those raw materials enter the process until they exit as a finished good, that's my flow time. So again, you're going to hear me inventory, throughput, and flow time. We're going to be, again, spending a lot of time on those. So as a flow unit moves through the process, one of two things happen, right? It undergoes an activity, so something is being done to it, or it's sitting there waiting for something to happen to it, okay? So when we draw those in a process diagram, typically we put the activities in rectangles, and we put what we call the buffers, where something's waiting. We make that a triangle. A lot of times my processes look a lot like rectangle, triangle, rectangle, triangle. I mean, it's just, so for example, raw materials coming in, right, they get received, that's an activity. Then they sit in the storage, that's a buffer. Then they get transferred to the production line, that's an activity, right? Then they may sit and wait at the beginning of the production line for something to happen. Then an activity happens on the production line. Then there might be a wait, or there might not be a wait between, if it's a continuous flow, right? It could just be one right after another, so you could have activity, activity, activity. Or sometimes we have buffers in between workstations, so it could be activity, wait, activity, wait, activity, wait. So it's rectangle, triangle, rectangle. So all of that's going on inside that our process boundaries. And then the output at the end is the finished good bicycle that we're shipping out. Okay. So flow time, again, to be specific, is the total time spent by a flow unit within those process boundaries. Flow rate, which is equal to throughput, right? So sometimes I think that's a little confusing when we're first starting out. The flow rate and throughput are the same thing. The way that I tell them apart when I'm reading a problem is flow time is always in a unit of measure of time, okay? If I write the problem, flow rate will always be listed as units per time, okay? Sometimes the textbook isn't always as clear about that, okay? But that's the way that you kind of try to distinguish the difference. So if I were to say, it takes 5 hours from the time it enters the process until it exits the process, that's flow time. If I were to say it's 10 units per hour, that's throughput, because it's how many units per hour, okay? And then, so flow rate or throughput is the number of flow units that flow through a specific point in the process per unit of time, okay? And then inventory is the total number of flow units present within the process boundaries. All right, so I give you the bicycle example. Now I want you to talk me through, think about like a Jiffy Lube. Let's use that as an example. What do you think what's the flow unit at Jiffy Lube? What would we say the flow unit would be? What is it that we're trying to watch at Jiffy Lube to improve upon? Julie is the only one that looks awake.
Would be how many cars they service?
Right. So our flow unit would be a car. Let's just start with that. That's one possibility for the flow unit we could look at. So if the flow unit is the car, right? So think about Jiffy Lube, and let's say it's a 3-bay Jiffy Lube, and there's some cars waiting outside. And we are going to define our process from the time that a car arrives at Jiffy Lube until the time that a car leaves Jiffy Lube. Okay? So all 3 bays are full, and we have 3 cars waiting. How much inventory is in our process? So we're defining our process from the time that a car arrives at Jiffy Lube until it exits the process. We have 3 cars waiting, and we have 3 cars inside being worked on. 6, right? That's how many cars are inside that process. Okay. And we could say that maybe we process one car every 15 minutes. Is that inventory throughput or flow time?
Flow time.
One car every 15 minutes.
Just kidding. Oh, throughput.
Throughput, right? Okay. All right. So, kind of getting that, and I do a different example because if I talk about bicycles and you go home and think, and you need to be thinking that through a little bit as we're going. Okay. All right. So again, our 3 process measures. I feel like I've hit them pretty hard. Flow time, the total time spent by a flow unit within the process boundaries. Flow rate or throughput, the number of flow units that flow through a specific point in the process. And inventory is the total number of flow units present within that. Okay. Inventory has traditionally been defined in a manufacturing context as material that's waiting to be processed or product, right? And so you're going to need to kind of reframe your definition of inventory for the class as we move forward, because sometimes we're going to be talking about the financial statements, we're going to be talking about dollars, right? And that's going to be inventory in our process, okay? Or if we're talking about a service, right, we can take a little bit different perspective. So our definition considers a general flow unit and therefore takes a much broader view. Whether it's a manufacturing facility, a service, a financial, or even an information process. Okay. So our definition of inventory includes all flow units within the process boundaries, whether they are in process or waiting to be. So whether they're actually something happening to them or they're in the buffer. And so what constitutes a flow unit depends on the problem under consideration. So we said the car, right? That's what we said. Another thing that we could do at Jiffy Lube is we could measure from the time that I spend money on raw materials, how long does it take me to get my money back from the customer, right? And so so our inventory or our flow unit there would be dollars, right? So I've spent money here. How long does it take for me to get it back, okay? And so and that's still the same company, but we're just looking at a different flow unit to try to gather some different information, okay? All right. So we acknowledge that inventory fluctuates over time, okay? And so we can look at instantaneous inventory buildup. So I can say what's happening right this minute, right? And so there's an example in our textbook on page 51 where we have a manufacturer of prefabricated garages. And so at time 0, the very first time that they take a snapshot, there's 2,200 garages, okay? They have production or inflow rate of the week of 800 garages per week, and the demand or outflow for the week is 1,200 garages. Pretty simple. I start with 2,200, I produce 800, I sell 1,200, that leaves me with 1,800 at the end of the week, right? That's a common sense thing that we worked with on our MRP problems in 343, right? It's just here's how we're going to calculate that inventory. And so we can look at that over time, right? And so here's that first week in the first column, and then what happens the second week, the third week, etc. Right? But our average production is 1,000 units, and our average demand is 1,000 units. So our average change is going to be 0, right? Because the difference between those two is 0. So that's telling us that we have a stable process. It may not be from one week to another, but over time it is stable. Okay? So now I want to bring in that discussion question. So I can look at this in terms of averages, and I can see that it's a stable process over time. Okay. Am I always going to want to look at averages, do you think? No, why not? The no was easy, but why not stuff? So let's think about the financial aid office, right? If I were to look at the average of the number of calls that they receive over the semester, would that seem like a big deal? I mean, how many they receive on an hourly basis? If you pick 3 days at the beginning of the semester, right, do you think that that's a much bigger deal, right? So sometimes we want to look at peak because it matters, right? Sometimes it's really about averages, okay? So as you do your project, you're going to have to decide, do I want to look at averages overall or do I want to pick some peak time periods, right? When we look at the university bookstore, if I look at averages, even on an entire day, it doesn't look too bad. But if I look at the specific time between 10 a.m. and 2 p.m., right, they can continue to build a line because they can't process students fast enough, right? So you have to kind of think about where those capacity issues might be. And how stable your process is going to help you determine that. Okay, so we know that a stable process is important. So it's defined as one in which in the long run the average inflow rate is the same as the average outflow rate. So, and at this point our text makes the transition from discussing flow rate to when we have a stable process, we can then refer to it as throughput. Okay, so it's the average number of units that flow into or out of the process over time. All right, so here we are to the it's Little's Law. Okay, Little's Law is so simple. It says that inventory in my process is equal to throughput times flow time. Okay, that's Little's Law, and you'll again be singing it in your sleep before the end of the semester. And then another measure here, and just we'll refer to it some. Inventory turnover is going to be your throughput divided by your inventory. Okay, so this chapter to me is more about Little's Law than it is inventory turnover. I want you to understand inventory turnover, but we're primarily focused on Little's Law. So Little's Law relating average flow time, throughput, and average inventory. So if we're asking about how long a typical flow unit spends within process boundaries, we're talking about flow time. And it's represented by a capital T in our equation, and it's a unit. The unit of measure for it is going to be time. On average, how many flow units pass through the process per unit of time? So we're talking about units per time, right? That's our unit of measure. That's our throughput. And on average, how many flow units are within the process boundaries at any point in time? That's our inventory. And our unit of measure is whatever unit we're measuring, okay? All right. So in a stable relationship, there is a fundamental relationship among inventory, throughput, and flow time. Inventory is equal to throughput times flow time. If we know two of the three measures, we can calculate the third, okay? Algebra. For a given level of throughputs in any process, the only way to reduce flow time is to reduce inventory, and vice versa. Okay? This becomes the first building blocks we utilize in mapping a process and identifying areas of opportunity. Okay? So the only way to reduce flow time is to reduce inventory. Okay? So if I have a level of throughput and I want to get it through my process boundaries any faster, the only way to do that is to take inventory out so that it moves through the process faster. Right? So think of this big storage room visual. So I'm Pella windows and doors, and at the end of the build season, I have, maybe 15,000 units in inventory, right? So I'm producing a unit off the end of the line. Let's say they were all the same unit. They wouldn't be, but let's say they were all the same. It would take 15,000 units would have to move before the one unit that I just produced would move, right? On the other hand, if I had no inventory, right, and it comes off the production line and it doesn't go into storage and it goes right to the customer, right, I have just increased that time by however long it would have taken. I have improved that time by however long it would have taken it to get through those 15,000 units of inventory. Okay, so again, the only way to reduce flow time is to reduce inventory. Okay, so what I want to do is go ahead and work some examples. And so to do that, I think I'm going to go ahead and come over here to the Elmo. It might take me just a little bit to get it set up.
Take this thing. Figure out how to get it out.
So if I'm going to go into chapter 3, the first thing I'm going to do is I'm going to go ahead and look at some examples from the textbook. And I'm going to start with the section 351. If I write like this, is that okay? Can you see that okay? Material flow.
Where are you?
I am on page 57. Okay? So it says a fast food restaurant processes an average of 5,000 kilograms of hamburger per week. Okay, so when I say 5,000 kilograms of hamburger per week, is that inventory, throughput, or flow time? Is it?
Throughput?
It's throughput. In the back row, very back row, is it Macy? What's your first name?
Chelsea?
Chelsea. Sorry, Chelsea. So yeah, so I'm going to just go, I'll start going around the room here, okay? So Troy helped us out with that. So that was throughput. So then Chelsea. Okay, then it goes on to say, typical inventory of raw meat in cold storage is 2,500 kilograms. So 25 kilograms of hamburger. Is that inventory, throughput, or flow time?
Inventory.
Inventory. Okay? And so in my world, I know that Little's law says that inventory is equal to throughput times flow time. Okay? And the question says, we're basically trying to understand how much flow time we have. So if I'm solving for flow time, it's going to be inventory divided by throughput, right? Which is going to be 2,500 kilograms divided by 5,000 kilograms per week, right? Which gives me my kilograms cancel each other out, and it becomes 0.5 of a week. Okay? And so what we're saying with that is, let me see if I can get that just a little bit better or not. What we're saying with that is then from a time that we get our inventory of hamburger in until the time that we use it, it's a half a week, right? If you owned a restaurant, would that be helpful to know, to be able to understand, right? Okay, so again, I knew 2 of the 3, so I was able to do that, right? So let's go ahead and then take a look at the next one, which is 352. Which is customer flow. So basically all we're doing in these examples is we're moving from one type of flow unit to another, right? And the first one we used, hamburger, was our raw material. And this one, the cafe something something in Belgium serves an average of 60 customers per night. Khalid, what does 60 customers per night represent? Inventory, throughput. What's that?
Inventory, I think.
Inventory, throughput, or flow time. So if I say customers per night, so my inventory would only be in terms of customers, okay? My flow time is only going to be in terms of time, and my throughput is going to be in terms of unit per time. So what is it? It's not inventory.
Then it will be throughput.
It's throughput, right? Customers per night represents a unit per time, and therefore that's throughput. Okay? So, Blake, it says a typical night is about 10 hours long, so that's just a note. A night is 10 hours. At any point in time, there are on average 18 customers in the cafe. What does 18 customers represent?
Inventory.
Yep. So that's saying I took a snapshot of my process, and there were 18 people in that process. So that being said, again, if I want to know, I've got inventory and throughput, so if I'm interested in flow time, it again is going to be equals inventory divided by throughput. So my inventory is 18 customers, right? And I can divide that by 60 customers per night, and I'm going to change my night to be 10 hours. So that being said, That cancels out to be 6. 18 divided by 6 is 3 hours. Right? So on average, that's how long a customer's staying in my restaurant is 3 hours. Right? So some pretty basic examples, but just to try to get our head around how Little's Law works and the different types of flow units that we can use. Okay? All right. We're going to do a job flow now, Julie. So a branch office of an insurance company processes 10,000 claims per year. Inventory, throughput, or flow time? 10,000 claims per year.
Throughput.
Yep, because it's a unit per time. And I'm going to use what we use to represent throughput as R. Okay, so I'm just going to start using R is equal to throughput. Okay, and then the next part of that says average processing time is 3 weeks. So we've got throughput, so Miranda, is 3 weeks flow time or inventory?
Wait, what did you say?
Just so if I said average processing time is 3 weeks, inventory, throughput, or flow time?
Just time.
Yep. So it's just going to be time because it's in that unit of measure. Okay? And so then if I want to know how long or how many claims I have in my process at any one time, right, I can calculate that by saying, okay, I'm interested in inventory, which is equal to throughput times flow time. So in this case, I have throughput is 10,000 claims per year. Okay, and flow time is 3 weeks. Anybody see a problem with that formula? What's my problem?
Need them in the same unit.
Yep, I need to change it to be the same unit of measure. And we're going to say 50 weeks per year. In a year. Okay, and so when I do that and finish it out, that tells me that I have 600 claims. And what that represents is I've just taken a snapshot of my process at any one point in time, and on average we have about 600 claims there. Okay? Again, is that helpful?
Do you just know that there's 50 weeks? Is that like
It says in the problem.
Oh.
Yeah, it tells me that in the problem. Yeah, sometimes you'll see 50 weeks, sometimes you'll see 52. Just okay. The next one we're going to do is a cash flow one. Okay? And so a major manufacturer bills $300 million worth of cellular equipment per year. Okay, so $300 millions per year. Abby?
is the throughput?
Yep. So $300 million per year. All right. So, and then if I continue to read, the average amount in accounts receivable is $45 million. So 45 million represents...
Is that inventory?
It is, because that's a snapshot of what's in there at any given time. In accounts receivable, and that's our inventory. Okay, and so we want to determine how much time elapses from the time a customer is billed to the time payment is received. In this case, the process is the manufacturer's accounts receivable department, and the flow unit is $1. Okay, and so Little's Law tells us that time is equal to inventory divided by throughput. So I have 45 million divided by 300 million per year. Okay, and if I finish that out, it's going to tell me that that is 0.15 of a year. And so one of the things we find sometimes is, I don't know about you, but that 0.15 of a year doesn't really tell me very much, right? So what I might want to do is convert that to months so that it tells me something a little bit. So I'm going to take it times 12 months per year. And then that's going to equal 1.8 months. So that tells me, on average, then it takes almost 2 months, 1.8 months from the time that I bill a customer until the time I receive payment from that customer. Okay? And so, again, that can be pretty useful information, you know, depending on what the standard is in your industry. Maybe you're above or below it, and it gives you a way to kind of give you a benchmark to say, okay, that's an area that we want to improve upon. Okay? But again, kind of our first blush at this was just to walk through and get some different flow units to get you used to the fact that it's not just a customer, it's not just a bicycle, it's not just a car, right? There's a variety of things that we can use this with, okay? Let me do a quick peek here. Okay, so let's go ahead and take a look at problem 3.1 in the back of the book, or in the back of this chapter. And 3.1 says, a bank finds the average number of people waiting in line during the lunch hour is 10. So what does that represent? Average number of people waiting in line is 10.
Inventory?
Inventory, because it's just people. On average, during this period, 2 people per minute leave the bank after receiving service. Chelsea, 2 people per minute leave the bank.
Throughput.
Yep. Right? So, again, we've said we now have, you're starting to track with the fact that 10 customers equals inventory, and 2 customers per minute is throughput. So if I wanted to know how long they spent, I would say T is equal to I divided by R. So my time is going to be 10 customers divided by 2 customers per minute. Tells me that they're there for 5 minutes. Right? So then we're going to do this last one, and then I'm going to stop here because I want you to be able to go and do the homework associated with this. This one adds just a little bit of a twist to it. So at the drive-through counter of the fast food outlet, an average of 10 cars wait in line. Khalid, 10 cars, inventory, throughput, or flow time?
Inventory.
Inventory. Okay. The manager wants to determine if the length of the line is having any impact on potential sales. A study reveals that on average, 2 cars per minute try to enter the drive-through area, but 25% of the drivers of these cars are dismayed by the long line and simply move on without placing orders. Assume that no car enters the line, leaves without service. On average, how long does a car spend in the drive-through line? Okay, so Blake, you get the twist. Okay, so the question is, we know that in this problem, 3.2, we say that our inventory is 10 cars. And it says the manager wants to determine if that line is having an impact on sales. A study reveals that on average 2 cars per minute try to enter. So 2 cars per minute would represent what?
Your throughput.
Right, 2 cars per minute. Except 25% of them are rejected. So what's my actual throughput? How would I calculate it?
B 2 times 0.25.
Or maybe that's how many are going to leave, so it'd be 2 times 0.75,
Yeah.
right? So that means that I've got 75% that are able to get in, right? So it's just a little twist on, we've got to calculate our throughput that way. So if that's the case, then I'm going to adjust that. So my flow time is going to be my inventory divided by my throughput. So inventory of 10 cars divided by 2 cars per minute times 0.75. And if I finish the math out on that, that should give me 6.67 minutes. Okay? So what you'll find is for the problems is your problems are going to be really tied closely to the examples that we do here in class. Like I'm not very creative because I want you to grasp the concept and then practice it. So it's going to be kind of a we do, you do situation on those discussion boards. So you're going to see very similar to what we did here in class today, just to reinforce different flow units, making sure you're looking at inventory throughput and flow time by those unitive measures, and then we'll build from there, okay? When I first started the class, I had students do the problems at the end of the textbook. But the problem with those are they do not directly tie to the examples that we do in class, and they usually have some twists and turns in them. And so rather than create twists and turns, we're just going to be pretty straightforward, and then we'll kind of do the twists and turns as some extra stuff here in class as we have time. Okay? So that's it on the MBPF book today. So, and you should be kind of into chapters 6 through 10 on the goal. So tell me what's going on with Alex. So 1 through 5, chapters 1 through 5. Alex, you met Alex, right? Did you meet his wife? I can't remember if you met her in this. Were they not getting along? Yeah, she was mad. Okay. And Alex went to a meeting, right? And the meeting was atrocious.
Yeah.
I actually have been listening to some podcast stuff, which is so I probably for all of you that's old hat, right? But I just got an iPhone here, so I've been doing my podcasts on there. And one of the podcasts that I just got was a whole hour on what a waste of time meetings actually are. Actually, how we should be using the tools that we have today to not sit down and do, not where we don't bring everybody together to sit down and update, but we communicate back and forth and we do it asynchronously, and how much more productive that is. And I thought of Alex when I was listening to that podcast and there's some truth to that. When I worked at Pella here in Murray, one week I did not go to a meeting, and my plant manager was really pretty annoyed with me. And he pulled me in and said, I need to understand why you weren't at this meeting. And I said, because I needed to get some things done this week. And he's like, well, what do you mean? And I said, I have 55 hours of meetings on my schedule this week. And I said, and clearly some of them overlapped and were at the same time. And I said, so if you want me to get anything done to support any of those meetings, I have to pick some not to attend. And he was like, well, let me take a, it's like, I don't think you believe me. But what happens is in that role, you're the liaison between the plant and the corporate offices. So you're in the middle of all that, And so again, I buy into that the meeting thing is not always the win. But so Alex has been to the meeting. What's going on in his factory?
Not good things.
Not good things. Has he met with Jonah yet? Yeah.
Yes.
And Jonah doesn't answer any questions.
Right.
It's always an interesting approach. Probably a good teaching approach, right? I'd probably be a better teacher if I could teach that way. I'm just not sure I'd be effective with that method. You'd have to come awake and ready to engage, right? That'd be the other part of that. So again, just kind of be working your way through the goal. Let's take a quick look at your calendar on Canvas here. Because I want to see when your projects are coming up. When you have to kind of have that first.
Was our meeting at 4:30 or 5?
5. 4:30 a.m. on there. We've missed it.
That's the only thing that's not crossed off on mine. It's like, you haven't been to this. I'm like,
Oh.
I didn't go at 4 a.m. Sorry. It's coming.
It's coming, I think. So there's this week the goal. So in 2 weeks from now, you need to have your process kind of identified that you're going to be doing your project on. So you need to be kind of putting that in the back of your mind. So I think, Blake, we heard you had kind of yours, and Abby, was it you the other one? So be thinking along that. If you have kind of an idea, Now's, like, today's a good time to stick around and let's talk about it for a few minutes. Not everybody needs to stay, but if you want to visit with me about your project, I'd like to have a chance to visit with each of you about your idea before you commit to it, because I think maybe I can help steer you in the right direction with that. So let's plan for that, and other than that, go do your homework, have a great weekend, and I'll see some of you tonight at the LSC Club meeting.
On there it says